Hi, and welcome to a video for Calculus 1 where we define the limit of a function algebraically and work through some problems to finish up this section. So in the previous video we went through the limit of a function graphically and sort of took a look at what does a limit even represent, and now let's take a look at some of these algebraic interpretations of the limit. So if I look here at question 3, for example, find the limit if it exists. Limit as x approaches 3 of the square root of x plus 1 minus 2 all over the quantity x minus 3. And what we should have seen in previous courses is if your answer was something like 1 over square root of 3, someone along the way should have told you that you needed to rationalize that denominator. And the reason for that is actually simplification. Long time ago, prior to calculators, that division of an irrational number was very difficult. And so instead, if we multiply, for example, in this example, by square root of 3 over square root of 3, so we get square root of 3 over 3. Now we're taking an irrational value and just dividing it by 3, which is much easier to do by hand. So nowadays I understand that since we have a calculator, we might not find a necessity to rationalize, but it's actually a very useful tool algebraically. So let's take a look at what we should do every time we run across a limit problem. What we should look at first is, can I just directly substitute in x equals 3? So I'm going to try to just substitute first every single time. And so if I'm substituting in 3 for x into my original problem, I no longer have a limit now because I'm evaluating that limit. I would have 3 plus 1 all under the square root minus 2 all over 3 minus 3. Now I recognize that that denominator is 0, right? But what we also have to recognize is we can't just stop there, right? Let's recognize what is the numerator. Well, the square root of 4 is 2, right? So 2 minus 2 is also 0. And so we run into the age-old calculus problem of what is 0 divided by 0. We should recognize 0 divided by 5, for example, as 0. We should recognize 5 over 0 as undefined. We should recognize then 0 over 0 as what? Well, if 0 was in our numerator, we said the answer was 0. Then we made the statement if 0 is in our denominator, it's undefined. But what if 0 is in both? Because we've also defined things like, well, any number divided by itself is 1. So is that true for 0? And in fact, no, this is actually called indeterminate. Basically, as of right now, I can't determine it. Okay? So we're going to spend a lot of time working on 0 over 0. 0 over 0 tells you that you have some algebra to do. So let's make a quick list here off to the side on what are some algebraic techniques that we're going to kind of stay within for algebraic limits. So the first thing that the first technique that we are going to limit ourselves to here for algebraic limits within Calc 1 is substitution. Sometimes if I can just substitute that number in, I get a value out, so I have my number that I put in, I've evaluated it, it's a two-sided limit, and it was exact, I'm done. All right, then we will see a factor in reduce or a simplify, if you like that terminology better. We will see LCD or lowest common denominator. And then we will see a rationalize. Now, if you are taking a Calc 1 course, you're pretty much going to stay within this sort of wheelhouse here for your algebraic techniques, if you will, to evaluate the limit. There are other algebraic techniques for sure, but for the most part, Calc 1 is going to stay within these four. Now, once you rationalize, then you can substitute typically. Once you use a common denominator and reduce it, then you can substitute. Then once you factor and reduce, then you can substitute. So our whole goal is let's get this expression simplified, reduced in its most simplest form, or rewritten in a different form that you might agree is maybe not looking more simple, but to where I can substitute that value in and figure out what that output might be approaching. So if I take a look back at my problem and I get 0 over 0, for right now, that's basically just telling me, okay, I know that I have some algebra to do. And I'm going to show you graphically what this looks like as soon as we're done, as well as we're going to test using our table of values to look numerically to make sure that our limit makes sense. But let's take a look at what this algebra is physically going to look like. So I tried substitution. I can't do that yet. I got 0 over 0, which means one of the factors should divide to 1 in the numerator and denominator. Well, I don't see factors yet. So what I'm going to do is use this idea of rationalizing, only I don't have necessarily an irrational value. I have square root of x plus 1. So what I'm going to do is multiply and rationalize this to see if something good can happen. So in other words, I do not want x plus 1 under a square root anymore. I can't just multiply by the square root of x plus 1 because then the square root will be attached to the 2. So what I want to actually do is move the square root from the numerator to the denominator. So in this case, I'm actually just rationalizing the numerator. Whereas in the example I began with, 1 over square root of 3, you were rationalizing the denominator for computation purposes. So we're going to rationalize the numerator. So I'm going to rewrite this problem and say limit as x approaches 3 of the original expression here, square root of x plus 1 minus 2 all over the quantity x minus 3. And I'm going to physically multiply this by the conjugate of the numerator, so the square root plus 2 over itself. Again, if I multiply by the same factor over itself, I'm really in essence multiplying by 1. I'm not necessarily changing its value, I'm just changing the way that it appears. So then again, don't forget to write down your limit, because if you don't write down the limit, you're only doing the algebra portion of this. You actually don't have the calculus portion, which is, I would argue, the most important part. So we should know how to multiply these conjugate pairs together. They do multiply to be the difference of squares, so it should just be x plus 1. Be careful, make sure you square the 2. So minus 4 all over. Do not multiply this out. I don't multiply out denominators until someone tells me I have to. And I'm going to show you the other reason you don't want to right now. We're trying to get to the point where we can substitute in 3 for x. I cannot do that in a factor that looks like x minus 3. So I'm really hoping that I can divide a factor of x minus 3 over x minus 3. Well, sure, because in my numerator, 1 minus 4 is going to turn into minus 3. So here's what my problem looks like if I just combine like terms in my numerator. Okay, this x minus 3 in the numerator is a factor. I will put a 1 in front of it just in case it's not clear, so I can divide those out. Now I have removed the discontinuity, or I've removed the 0 in both the numerator and denominator, so chances are I can actually evaluate this. So now that I'm going to the evaluation stage, I'm just going to say which is, and I'm going to substitute in 3 for x. So my numerator is just a 1, and my denominator would be square root of 3 plus 1 is 4, plus 2, square root of 4 is 2, so it should be 1/4. My limit should be 1/4. So let me show you what this looks like graphically and numerically using our calculator so we can verify this limit, because you should always have another method of checking this algebra that you just spent so long doing. All right, so if you go to your calculator, a couple things that I will continually remind you of throughout the course is anytime I'm going to use my y equals and I'm going to eventually use a table, I want to make sure that my table set or second window is set up so that my independent variable is on ask, and I'll hit enter there, because then when I look at my table, I'm able to type in whatever I want for x. Okay, so that way your table will look like mine. So for now, I'll go to y equals, and it's very important that you type in the very original expression that you were given. You're trying to find the limit as x approaches 3 of this irrational numerator here, x squared of x plus 1 minus 2 all over the binomial x minus 3, so I typed it in accordingly. You don't want to type in what you've simplified because you're trying to identify any potential errors that you have, so you want to make sure you're typing in the original. Then I want to pay attention to where I'm looking graphically. I'm looking as x approaches 3. So if you're in a standard window, x is probably going from -10 to 10. That might be pretty large considering you're only focused on x approaches 3. So look what I'm talking about. If I just hit graph, well, here's 1, 2, here's x approaching 3. I can't necessarily tell if that's 1/4 or 1/8 or 0 or what that is, right? It's very, very difficult for me to see. If I wanted to see it graphically, I could do something like just surround x is approaching 3. So something like go 2.9 to 3.1. And if you want to see the tick mark at 3, you can count by 1/10 because then it's going to show you that tick mark. I also noticed that I didn't need y values going from -10 to 10. They looked very, very small. So I could probably, and I'm sure I can go even smaller, but I could probably get away with going from y min of -1 to a y max of 1. Again, those are your vertical sort of walls here. So now when you hit graph, your bottom of your graph here is -1 and the top here is +1. So you'll notice a couple things now when I look at the graph. Now it's still not necessarily clear that that's 1/4. I'll show you how I get that graphically here in a second. But I can also see that there's a hole right there that is not just a glitch on my calculator, that is actually trying to help me see that there is a jump or a discontinuity as x is equaling 3. But again, good thing we're just trying to evaluate the limit, or where is this hole in this particular graph, and it would have a y value of 1/4 when x equals 3. So what I could do, a couple different things. I can try my calculate menu. I'm a big fan, and so are most of you. So second trace, calculate, and I don't think a lot of people use this first option enough. I want to calculate a specific value, so I'm going to hit enter. I think I know the x value that I want to calculate at. X equals 3. So I hit 3, enter, and my y equals is blank. And that's because that's a hole, so my function's never going to be able to be evaluated at x equals 3. Remember, when we substituted in 3 from the beginning, we got 0/0. But what I can do is I can calculate a value at 2.999. Ooh, look at that. It's the y value is 0.25001. That's very, very close to 1/4. So my left limit, or my left-sided limit as x is approaching 3, looks like it's 1/4. Then I can calculate the right side, calculate a value, 3.0001, for example, or however close you want to get. That's now my right side of 3, And that also appears to round to 0.25, which is in fact 1/4. You can also see this using your table. I would just type in 2.999 and then 3.001. I caution you because sometimes let me try putting in 3.000000001, and sometimes it'll show me exactly 0.25 in the table, and that is not exactly 0.25. It's just such a close rounding that that's what they're showing me. Other times it shows me 0.25 because of the width of my table. So if I actually hover over it, I would see something like 0.249999999. Okay? But I kind of verified graphically and numerically that that 1/4 does in fact make sense, and that that's the limit for that problem. All right, since I have my graphing calculator out, I'm going to jump down to this next problem here. Find this infinite limit. Well, and if it has the word infinite in the directions and you don't see an infinity in the question, it's probably gearing you towards, hey, the answer might be one of the infinities, or maybe even it does not equal. What I want you to notice about this problem is if I reference that algebraic list of different techniques that I can try algebraically to evaluate any limit, I see substitution, factor, LCD, and rationalize. They all kind of lead me to the substitution. So if I look at the problem I'm given now, it's definitely not a rationalized problem. Nothing is irrational here. It's not a factor and reduce problem. Everything is in factored form, and I can't divide any factors out to be 1. And there's no LCD to really be had here. So I'm going to go right to the substitute and see what I get. So I'm going to substitute and say, what if x is equal to 1? Well, then I get 2 minus 1 over 1 minus 1 quantity squared. I have 1 over 0. Now in the past, we've just said undefined. That's not going to necessarily be good enough. That's not the limit of this function as x approaches 1. So what I'm going to need to do is look at sided limits. And again, this needs to be two-sided as x approaches 1 from the left and as x approaches 1 from the right. What are those limits? And then I can also use my table or graph to help me out. So let me grab my calculator and type in this function. All right, when you do type in this function, be cautious about your parentheses. For that numerator of 2 minus x, you want all of it to be in your numerator divided by the quantity x minus 1 squared. And now before I hit graph, I'm just going to hit zoom 6 because that's going to put me back on that standard -10, 10, -10 to 10 window. And I'm looking as x approaches 1. So I can see, even though they didn't draw it in for me, I do have a vertical asymptote here at x approaches 1. So I'm going to draw what I see here on my paper, and I'm just going to use a screenshot. Okay, so here we are. So now I can see that as x is approaching 1, I sort of have this vertical asymptote right here at x approaches 1 that they don't necessarily draw in for me, but I can see it. Because as x is, for example, 0.999 and approaching 1 from the left, I'm going up here to positive infinity. My graph is approaching high values, like positive infinity. And as x is approaching 1 from the right, and as I'm moving in from the right-hand side of this graph, I can see that it's also going up to positive infinity. Therefore, my two-sided limits are the same, so I can say this is approaching positive infinity. Again, the other way to look at this would be to look at your table of values. So I'll do that with you quickly. And so if I go back to my table now, I'm not necessarily, second table, I'm not necessarily looking at those values surrounding x is approaching 3. I'm looking at as x approaching 1. So you can delete, 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 which is right next to your arrows if you like a clean table to start with. And then I can say, obviously, if I type in x equals 1, I'm going to get an error because I cannot evaluate my function at 1, I got 1 over 0. But I can do one from the left, 0.999, and x approaches 1 from the right is 1.001, for example, and 1e6 is scientific notation for 1 times 10 to the 6th, very, very large number, especially when you consider that normally we look at our graph from negative 10, 10 to negative 10, 10, and this is, 1 times 10 to the 6th. And then the other is 999,000. So they're both approaching very, very high numbers very quickly. So the closer I get to 1, the closer I will see that approaching positive infinity. So I hope that helps you get started. There is going to be a part 3 video where we investigate some more limits algebraically.